Get out of there. Cool. All right. Hey guys. So today I'm going to talk about the constant speed propeller and governor system. I'm flying a PA-44 Piper Seminole. It's a big training multi-engine aircraft. So again, this is a rough illustration that is not to scale of the constant speed propeller and governor system for that model. Now your plan might be a little bit differently, but the principles should be roughly the same for a constant speed propeller. So just doing that disclaimer now, don't go to your maintenance guy and be like, where's this? And if you have a different model, he may be like, what in the world are you talking about? So going to give the basic rundown of the system components, as well as some basic aerodynamic principles. And then we'll get into this system, but just hopefully so you can have a baseline understanding of what we're talking about so that this will make a lot more sense. So first things first, this is literally the propeller governor system. It's a little tiny black box. It's about, I don't know, maybe 3 inches by 4 or 5 inches, depending on, again, model. And it sits just aft and above of the propeller hub, again, on Piper Seminole. So I won't say Piper Seminole 1,000 times, just saying it a bunch now so that we're all on the same page. But this is what it is. It's this itty bitty guy. I can't see most of the components in the actual system. There are a couple things that we can see, and I'll point those out whenever we get there. Another thing is you may have seen a chart similar to this. There's these all over the internet and a couple FAA approved documents. So like the PHAC has a kind of similar drawing. But this didn't really make much sense to me whenever I first learned about it, and through some extensive research, which led to this craziness, I wanted to figure out exactly how this system works. And now I do. So hopefully I can relay that onto you, and hopefully it'll make a little bit more sense to you, because this things not actually moving makes it really hard to understand. So again, hopefully this will make things make sense. So we've got a couple sets of levers in the cockpit. This is our, one second, let me cancel this. I'm just going to lock everything up so I can't mess with it. A couple sets of levers in the cockpit. So we've got our 3 levers. We got our black, our blue, and our red. Red is mixture control. We're not really going to talk about that too much. But the black control is the throttle, and that's not shown here because the big thing that we want to talk about is our propeller RPM control, which is our blue lever. We will touch a little bit on what the black one does, but for the most part, this is the meat and potatoes of what we were going over. So first things first, major components is we've got our engine here. Engine doesn't look like this. It looks like that. But for the sake of my memory storage and this thing crashing, I hope it doesn't crash this video. Hopefully we can get through without it crashing, but it doesn't like all these shapes. Anyway, if that happens, that's why. But anyway, our engine is turning our crankshaft. And now for this specific engine, this is spinning in the clockwise direction, a conventional twin engine. Both of the engines spin clockwise. Now, non-conventional, the rat engine spins counterclockwise, but for the purposes of this, this engine is spinning in the clockwise direction. So anytime you see engine-driven anything, it always means that it's geared off the crankshaft. So engine-driven oil pump, this is this blasphemous-looking gear right here. Gear, rotating pilot valve, and we'll get to that in a moment, as well as rotating the engine-driven oil pump. So if we do not have engine power, we do not have this oil pump, period. Nor do we have our engine-driven fuel pump. That's why we have that auxiliary auxiliary fuel pump in case we lose engine power. Nothing is turning these engine-driven items. So that's an important distinction, and we'll get into that in a moment. But essentially, crankshaft spinning clockwise, right? And then we get to our prop hub, and this is all hidden underneath the nose cone. But if you go into your like maintenance hangar, they may have the cone ripped off, or if you take care of your own plane, you can take it off yourself. And you really can't see all of this that's inside of the prop hub. It's all kind of encased in the like prop casing, essentially. But this is a cross section, and again, not to scale. And I'm not an engineer. I'm just a humble student that used this to make more sense of the system. So it may look a little bit different in the plane, but hopefully the principles are roughly the same. So in this specific constant speed propeller system, it's not the same as a fixed pitch propeller. So if you flew like a smaller GA plane, these propellers don't move. They stay locked in there, bolted into the prop hub, and maintain the same angle, which is fine and dandy. But it's not the most efficient. So this constant speed propeller takes care of some of those inefficiencies in a couple ways. And I'm not going to go super into like efficiency. Just know that this guy is more efficient. That's the gist. More aerodynamic when it needs to be, less aerodynamic when you don't want it. So for multi-engine props, it's huge. So in this specific model, it has a feathering propeller. So this propeller wants to be in a feathered condition as opposed to a windmilling condition. So what are those conditions? So a feathered condition would be if this prop, instead of being here, was rotated to where it is slicing through the relative wind to the plane's forward motion. So plane's moving this way, relative this way, and this propeller would be rotated, so it's literally slicing through the air, so less drag. So if we were to lose one of our engines, so say this is our left engine, this is our right engine. Say we were to lose this engine. Sorry, I'm going to make this make sense maybe. If we were to lose our left engine, and it's sitting here spinning in the wind, picking up a whole lot of drag, but it's not creating any lift. And this guy is going full power. We will yaw towards the inoperative engine. Now, we have a feathering prop, so our prop actually wants to be in a feathered state, so it's directly into that oncoming wind, taking off a lot of that drag, so there'll be less of a yaw to the inoperative engine. There'll still be some yaw there, and we correct that with our rudder, of course. But this feathering system is essentially to get rid of that excess drag so we can maintain directional control of the airplane should we lose an engine. So a couple things that are trying to feather this prop. Big three are this nitrogen charge, our feathering spring, and our counterweight. So I'm going to go into each one of those. So nitrogen charge, just a fancy way of saying pressurized nitrogen in the nose cone. So it's powered up to roughly 40 psi, again, per my model. And that is essentially acting as a cushion. It's not the back end of this, or I say forward end of this spring right here, essentially cushioning any changes that happen. It's not going to put a bunch of wear and tear on the prop hub. It's kind of like a little cushion, right? But it is pressurized, so it's not giving too much. Then we have our feathering spring, which is this guy. And this guy's a big old spring, like super heavy. It's kind of crazy to me that oil can press against it because it's a big spring. But it's pressing against this. I'm calling this a pressure plate for this demonstration. I don't know the technical term for it. I've been unsuccessful in finding what separates oil pressure from that spring. If you guys know, please let me know. But we're going to call it the pressure plate for this demonstration. So, sorry, that was red. It was getting annoying. Cool. Pressure plate. So this pressure plate, based on the pressure of this spring, is trying to push this pressure plate aft. So if this pressure plate is fully aft, our propeller will be fully feathered. It's just the gist of it. So these little feathering actuators that I put here, that's not, again, not the technical name for them, but it's essentially what it is. Depending on this pressure plate, will change per this little actuator the angle of the propeller. So we want to control where this plate lies. So more oil pressure would be squeezing the spring, causing the propeller to be more unfeathered. And the further aft it goes, the more feathered it is. So another thing we have is our counterweights. And these counterweights are mounted on the actual propellers themselves. So our propeller is spinning clockwise. These counterweights sit on the outside of that turn to essentially pull on the propeller, trying to feather it while it's turning. So they're just there, just an extra parameter to try to feather the prop. So those are the big things trying to feather. And this is that feathering motion. So pulling this leading edge into the relative wind of the plane's motion. The same with this one, turning this way, pulling this leading edge into the relative wind. So that's everything that's trying to feather our prop. Now, we don't want it feathered. We want it feathered if we've lost an engine, but if we're trying to produce thrust, we do not want it feathered. And that's because the relative wind that matters to us is this guy. So this is a rough angle of attack. Again, I couldn't quite make an airfoil on this. That was more technically advanced than I am. So it looks like a propeller, but it's just a big old yellow piece of plastic. But a rough angle of attack is from this relative wind to the chord line of this. So we have a roughly, 30-degree angle of attack. Now, if our propeller is feathered, it'll be at a 90-degree angle to this relative wind, just slapping away at this wind and not creating any lift at all. It's not going to create lift that way. Whereas if it was windmilled, so completely directly into this, slicing through this wind, it won't be creating lift that way either. It'll just be spinning and creating a lot of drag from this forward motion relative wind. So we don't want this windmill, really ever. Feathered is good for certain applications. So if we turn off one of our engines for training flight, we want to have it feathered to have that, to not have as much drag. Cool. So that's all the feathering stuff. Oh, and this is a hollowed out portion of the crankshaft going into the prop hub, and that's where oil sits. And this oil pressure presses against that pressure plate. So it actually is in the crankshaft. It's not elsewhere. That's, again, something I've found. Again, how this goes into the crankshaft, I don't know. I haven't haven't been able to find exactly how this is geared, but this is a kind of rough estimation of how that would work. So separated oil going in to this kind of chamber and having higher oil pressure. Again, this is how the system works. It's not how it's made. So, cool. Now this guy. This is the big whole shebang right here. And this is that little black box that we showed a second ago. And this is our prop governor. So, propeller governor has a few main components. So, first off, we have a engine-driven oil pump. So, as our engine is spinning, this is pumping oil from our engine oil sump, which actually sits below the engine, and pulling oil into the prop governor system. So, high pressure oil into this. And now we have our prop lever, the blue guy, and that is increasing tension or decreasing tension on our speeder spring. And that's this guy. So the more tension we have on this spring, we'll push this little, and again, I'll call it another pressure plate down or up if there's less tension. So if we push our propellers fully forward, it will push this pressure plate down with more tension on that spring. If we pull our propeller lever fully aft, it will decrease tension on the spring, forcing the plate up. So if we pulled our engine to, again, simulate an engine failure, it would pull up to here. It would just be completely out of the system. So speeder spring, cool. And our speeder spring connected to that plate. The plate is connected to our pilot valve, which is this little, again, doesn't look like this, but it looks kind of like this. And where this pilot valve is located will change what oil is doing. So in a neutral position, our pilot valve is blocking this feeder line, which goes into the prop, essentially sealing whatever oil pressure we have set in here. Now, say we go to our propeller lever and push it forward. So we want more RPM. Say we're at 2200 and we want to go up to 2500. We increase tension on this spring, which pushes the plate down. Now, I don't know if you're familiar with that other diagram here, but whenever we're in this condition and that plate is down, these flyweights are pushed in, that is called an undersped condition. Does it have it here? Yeah, underspeed. Sorry, underspeed. Cool. Don't freeze on me. Okay. So these flyweights, again, I'll zoom in kind of on them. This is a flyweight, and it's a little L-shaped bracket. It is mounted to a hinge, so it can swing freely. These other colors are just different positions that they can be in, so hopefully that's not confusing. But they are mounted to this disc, and this disc spins, when you get the direction right, spins at the same rate, or it might be geared down a little bit, but it spins with the engine. So if the engine's not spinning, this guy isn't spinning. So we've added 300 RPM, go from 22 to 23. We've pushed the prop lever full forward, increasing tension on this spring, forcing this down. When that happens, this opens up this little oil line. So that pressurized oil that's in this chamber gets forced into here, increasing the oil pressure in this chamber, pushing this pressure plate forward. So what does that do? It makes our prop more unfeathered, right? So we want higher RPMs, okay? So this propeller, by being more unfeathered, will decrease its angle of attack to its relative wind. So that does a couple things. One, it's not producing as much lift, right? You would think oh, it's a lower angle of attack, there's less force. Well, yes, but there's also a lot less air resistance to that propeller moving. So this propeller will move faster through this relative wind, increasing its RPM. Okay. So as the propeller speeds up, these flyweights that are spinning super fast, the top part is heavier than the lower part. So centrifugal force that was here is going to pull that heavier side out, forcing this plate up. And it may go past. It may go past into an oversped condition. Say you have an abrupt prop setting change, right? So it's going too slow and now it's going too fast. But then eventually it'll kind of equalize out and sit here, blocking this off and maintaining that constant oil pressure. So again, just for sake, say we drop from 2500 to 23, we release tension on the spring, pulling the plate up. That allows these flywheels to spin up, right? Because these things are always touching each other for the most part. But depending on the tension of the spring dictates where that equilibrium will sit with the flywheels. So yeah, we've pulled our prop lever aft to decrease tension on the spring, pull the pilot valve up, and that allows this excess oil pressure in here to escape the prop and go back into the oil sump. As that happens, as we said, less oil pressure, pressure plate moves aft, further feathering the prop. So it will move from this position to being more feathered, which again, against this relative wind, will be more air resistance. So the propeller will start slowing down. And as it slows, we get back to that new equilibrium, blocking off whatever RPM, whatever oil pressure setting makes sense for the RPM setting we have set. So cool. That's the basic rundown of how underspeed and overspeed conditions work. Now, what happens if we lose an engine? So for the sake of this, just training, we've turned off our engine intentionally, right? Pulled our mixture to idle, at a safe altitude. This engine sputters out, it stops moving. That affects a couple things. First things first is this gear stops moving, which means these guys are no longer spinning, and our engine-driven fuel pump is no longer spinning. So this whole thing, you would think, just shuts down. So we pull our propeller control completely aft, so we release all the tension on this spring. So in that condition, right, we pulled it aft, pilot valve goes up, and all the oil pressure comes out of this feeder line, allowing this pressure plate to go fully aft. Now, whenever we enter, we feather our engine intentionally, right? We pull it back into that little detent, and that actually allows the prop to fully feather, to have less drag. So we've got no oil pressure here. This guy is fully aft. These guys aren't spinning. Engine-driven oil pump is out. This guy is out. Our pilot valve is essentially just out here in limbo. So as our engine was running earlier, this engine-driven oil pump was pushing oil through this system and accumulating excess oil pressure in this thing called an unfeathering accumulator. It does not look like this. It's a big old tank mounted to the firewall. But for illustration purposes and the memory of this VR headset, it didn't like the big tank, so small tank. But essentially, it gets that excess oil pressure. When we feather our prop, when we pull it back into that detent, this little trap door right here shuts, locking in that excess oil pressure, so that whenever we lose pressure, it's not pulling it out of here. It stays. This is our little safety net. So we want to restart the prop in the air. So no oil pressure in here anymore. This thing is all the way empty. This guy's all the way aft. And this guy is fully, and this propeller is fully feathered. So if we tried to bump our starter, say we pumped up our mixture, we hit the prop and we didn't have this guy, it wouldn't get out of that feathered condition very easily, and it would be really hard to start rotating against this relative wind when it's essentially just a paddle, right, in that feathered condition. So we want to get the propeller unfeathered before we actually start it. So say we bump the mixture up, turn the mags on, give ourselves like maybe an inch of power to not overspeed the prop initially. But then we take our prop lever and we push it full forward. So as we push full forward, more tension on the spring goes down here. That opens up this line again. When we do that, that trap door pops open, and all that excess oil pressure that's been built up, along with that nitrogen charge pushing it, forces oil into the system through the feeder line and forces this pressure plate forward. When that happens, the propeller gets slightly unfeathered, catches this relative wind, which forces the propeller to start rotating. When it starts to rotate, a couple things happen. One, our trusty gear here starts spinning, engine-driven oil pump starts spinning. Our mags pick up that rotation and start our engine. And then our flywheel or flyweights also start spinning, forcing, and then eventually, whenever they're strong, moving fast enough, force our pilot valve back up, locking in that oil pressure, and the system starts again. So that's roughly how the constant speed propeller and governor system works. Um, this building this whole thing really helped me understand the system. I'm hoping that it helped maybe you if you've had issues with it. It's a pretty cool system. I just love how tiny it is on the plane and that it can control this giant propeller. Just these small, minute changes, and I mean, it's all has to do with the little positioning of this pilot valve. So, again, hopefully this made sense. If you do have any questions or complaints, please let me know in a comment. I'm always down to learn. So, tips, tricks, especially for GravitySketch, which is what I'm doing this in, please let me know. All right, thanks for watching.